Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Imagine waking up one morning to a world that no longer works the way it should. Your smartphone can't find a signal. GPS satellites are lost in space. Commercial airliners reroute mid-flight, not because of storms, but because the planet's magnetic field has become unpredictable. Even the birds seem confused, flying in erratic patterns, and the brilliant auroras that once danced above the poles now flicker over cities thousands of miles from their usual homes. It sounds like the beginning of a science fiction thriller, but this unsettling vision is rooted in very real science. Deep beneath the surface of our planet, something remarkable and potentially dangerous is taking place. Earth's magnetic field, our planet's invisible guardian against solar radiation and cosmic chaos, is showing signs of strange behavior. And some scientists believe it may be on the verge of a dramatic collapse. The magnetic field is generated by a process known as the geodynamo, a natural engine powered by the movement of molten iron and nickel in Earth's outer core. This dynamic flow creates electric currents, which in turn produce the magnetic field that extends from the planet's interior into space, forming a protective bubble known as the magnetosphere. It's this barrier that shields our planet from the solar wind, a constant stream of charged particles emitted by the sun, and from high-energy cosmic rays that can damage DNA, disrupt electronics, and alter atmospheric chemistry. Without this shield, Earth would be a very different and far more dangerous place. But here's where it gets truly fascinating. Over the last 180 years, since scientists began systematically measuring the strength of the magnetic field, it has weakened by nearly 10%. That might not sound like much, but on a planetary scale this is significant. More alarming still, areas of particularly low magnetic intensity, like the South Atlantic anomaly, are expanding. The South Atlantic anomaly is a vast stretch of weakened magnetic field over parts of South America and the Southern Atlantic Ocean. Satellites passing through this region frequently experience glitches and equipment failures due to increased radiation exposure. Even the Hubble Space Telescope has to shut down sensitive instruments when flying over this area. Why? Because the weaker magnetic field there allows more energetic particles from space to get dangerously close to our orbiting technology. It's not just the field strength that's changing, it's also the direction. The North Magnetic Pole has been shifting dramatically, moving from northern Canada towards Siberia at a speed of over 30 miles per year. For context, that's more than 54 kilometers annually, more than 10 times the average historical drift rate. This rapid motion forced scientists to issue an early update to the World Magnetic Model in 2019, the global map used by everything from military navigation systems to smartphone compasses. What's driving this pole migration? Some experts believe it could be linked to complex changes in the liquid metal flows deep beneath the Earth's crust, changes that may signal the beginning of a full magnetic reversal. Full reversals have happened before. In fact, Earth's magnetic poles have flipped many times in the past, on average about once every 200 to 300,000 years, but it's been nearly 785,000 years since the last full reversal, known as the Brunhes-Matuyama reversal. The timing suggests we could be overdue for another. However, magnetic reversals don't follow a predictable schedule. Some happen quickly, over just a few thousand years, while others take tens of thousands. During these transitions, the field doesn't disappear entirely, but it can become significantly weaker and more complex, with multiple north and south poles emerging at different locations across the globe. Imagine compasses spinning like roulette wheels and solar storms punching through weakened regions of the magnetosphere, wreaking havoc on modern electrical infrastructure. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free and it helps us grow this community together. Now let's go even deeper, literally. The core of our planet is a cauldron of extreme physics. About 1800 miles beneath your feet lies the outer core, a layer of molten metal swirling at thousands of degrees Fahrenheit. It's here that the magic of the geodynamo happens. The intense heat escaping from the inner core drives convective currents in, the liquid iron-nickel mix. At the same time, Earth's rotation causes these molten metals to spiral and twist in columns aligned with the planet's axis. This motion generates electrical currents, and those currents generate magnetic fields. It's a feedback loop, a TTOA, self-sustaining magnetic engine that has powered Earth's field for over 2 billion years. But if this dynamo engine were to slow down or become unstable, the magnetic field it generates could falter. And scientists are starting to see signs of such a slowdown. Studies using data from the European Space Agency's SWARM satellites, a trio of orbiters launched in 2013 specifically to study Earth's magnetism, have detected unusual changes in the strength and structure of the field, especially over the South Atlantic anomaly and beneath Africa. One hypothesis suggests that a growing region of reversed flux deep in the core may be tugging at the field, destabilizing it. Another theory proposes that asymmetrical heat flow at the core mantle boundary could be interfering with the convection currents, effectively choking the dynamo and reducing the field's power. The consequences of a magnetic field collapse would ripple far and wide. Without a strong magnetosphere, solar storms could trigger blackouts, fry satellites, and expose astronauts to dangerous radiation. The infamous Carrington event of 1859, a massive solar flare that disrupted telegraph systems across Europe and North America, would pale in comparison to what a similar storm might do today. A modern-day Carrington event could cripple the global power grid, destroy billions of dollars in electronics, and disable communication networks worldwide. But here's something curious. Despite the dramatic risks, previous magnetic reversals don't appear to have caused mass extinctions. Life on Earth in all its resilience has survived them. That said, no prior reversal occurred during a time when human civilization depended so heavily on magnetic field-sensitive technology. We're entering uncharted territory, not just geologically, but technologically and biologically. The question remains, are we truly on the brink of a collapse, or are these fluctuations part of Earth's natural rhythm? That's what scientists around the globe are racing to understand. Some geophysicists argue that the current weakening is still within the range of normal variation, while others believe we may be entering the early stages of a major magnetic event. The answer lies hidden deep beneath the crust, in the molten metal that holds the key to Earth's magnetic destiny. Beneath our feet, where sunlight never reaches and pressure mounts to unimaginable extremes, Earth hides a secret engine, one that has turned uninterrupted for billions of years. This is not the kind of engine built with pistons and gears, but a vast churning ocean of molten metal. It's here in Earth's outer core that the geodynamo lives. It breathes magnetic life into our planet, forming an invisible shield that stretches far into space. But what if that engine were slowing down, sputtering, showing signs of instability? Could this be the beginning of the end for the magnetic field as we know it? Let's dive into this subterranean world. Roughly 1,800 miles beneath the surface lies the outer core, a layer about 1,400 miles thick, composed primarily of liquid iron and nickel. The temperatures here are staggering, ranging from 4,000 to over 6,000 degrees Celsius, hotter than the surface of the sun. The inner core, a solid sphere of mostly iron about 760 miles in radius, is encased by this fiery sea. The temperature gradient between the hotter inner core and the cooler outer layers of the planet drives convection. Massive, heat-driven flows of liquid metal, rising and falling in an endless cycle. But this isn't just any fluid motion. Earth rotates, and that rotation induces the Coriolis effect, twisting the convective plumes into columns that align with the planet's axis. These moving columns of conductive fluid generate electric currents, and by the laws of physics, specifically Faraday's law of electromagnetic induction, these currents generate magnetic fields. As the currents move and the fields grow, they reinforce each other in a positive feedback loop. That, in essence, is the geodynamo. Now, here's where things get intriguing. Studies of seismic waves, those created by massive earthquakes, allow scientists to peer into the depths of Earth's interior. And in 2023, a seismic analysis from the University of Southern California revealed that the inner core may have recently slowed down in relation to the rest of the planet. For decades, the inner core was thought to spin slightly, faster than the Earth's surface, a phenomenon known as superrotation. But now data suggests that it may have not only slowed, but reversed direction. That is, it may be rotating slightly slower than the mantle and crust above it. This phenomenon is still being hotly debated in the geophysics community, but if true, it could have profound implications. A slowdown in the inner core's rotation could alter the dynamics of heat transfer between the inner and outer core, thus changing the flow patterns of the molten metal in the outer core. If convection is disturbed, even slightly, it can impact the structure and intensity of the magnetic field. Scientists from the Institute of Geodesy and Geophysics in Wuhan, China, have modeled how these inner core fluctuations might relate to periodic weakening of Earth's magnetic field. Their findings suggest that variations in the rotation speed of the inner core could coincide with dips in field strength and even foreshadow reversals. This isn't the first time Earth's magnetic engine may have stumbled. Roughly 42,000 years ago, during what's now called the Lachamps excursion, the magnetic field weakened dramatically, down to just 5 to 10% of its current strength. For a brief period, it flipped polarity, with the North and South poles swapping places, only to reverse again a few hundred years later. This period, which researchers have dubbed the Adams event, may have had far-reaching consequences. Studies of ancient tree rings from kauri trees in New Zealand show spikes in radiocarbon levels, evidence that cosmic radiation bombarded Earth's atmosphere during this magnetic crisis. Some scientists believe this radiation influx may have contributed to climate shifts, extinction events among large animals, and even the sudden development of cave art, as early humans sought shelter from increased ultraviolet exposure. So, could it happen again? Today's satellites, like the European Space Agency's SWARM constellation, are monitoring Earth's magnetic field in real time, mapping its strength, direction, and anomalies. These observations reveal areas where the field is growing weaker at an alarming rate. The South Atlantic anomaly, for example, has been expanding for decades, and some scientists believe it could be the harbinger of an impending global reversal. The weakening field beneath southern Africa also raises questions. Could these be the birthplaces of a new magnetic pole? Or are they transient features, part of a chaotic but ultimately stable field? Here's where we face the limits of our understanding. The geodynamo is an incredibly complex non-linear system. It's influenced by heat flow, composition, pressure, rotation, and even mantle dynamics. Computer simulations, like those run by the National Center for Atmospheric Research, attempt to model the behavior of the core using supercomputers. These simulations suggest that even small asymmetries in heat flow at the boundary between the core and mantle can shift the behavior of the entire magnetic system. For instance, hotter regions beneath the Pacific or Africa could disrupt the convection cells that drive the field, creating anomalies and weakening the overall strength. And here's the kicker: when the magnetic field begins to falter, it doesn't do so evenly. It becomes unstable, turbulent, and fragmented. Instead of a single dominant dipole with one north and one south pole, you might get multiple magnetic poles scattered across the globe. That's exactly what simulations and paleomagnetic records suggest happened during past reversals. The magnetic field could flip in stages, with transitional fields lingering for thousands of years. During that time, the planet would be far more exposed to solar and cosmic radiation. For life on Earth, especially in the modern era, this is not just an academic curiosity. Airline routes could shift, communication satellites could fail, radiation exposure for astronauts could increase dramatically, and even animal migration could be disrupted. The technology we take for granted, GPS, radio communication, internet, relays, depends on satellites that are vulnerable to geomagnetic storms. And if Earth's magnetic field weakens significantly, more charged particles from space could reach those satellites, inducing electrical currents that fry circuits and disable systems. And what about Earth's atmosphere? The magnetic field plays a role in keeping our atmosphere anchored. Mars, for example, once had a magnetic field, but when it lost it, the solar wind gradually stripped away its atmosphere, turning a once Earth-like planet into a barren wasteland. While Earth's gravity and atmosphere are much more robust than Mars, a severely weakened magnetic field could still affect the upper layers of our atmosphere, allowing high-energy particles to alter chemical compositions, possibly affecting ozone and increasing UV exposure on the surface. The implications are staggering. A change in the inner core's spin may sound like a distant, abstract idea, but it could be the first domino in a chain of geophysical events with global consequences. Earth's engine is not a constant. It evolves, it pulses, it flows, and sometimes it stumbles. Imagine waking up to a sunrise that doesn't quite rise where it used to. Your compass points not north, but somewhere near Indonesia. Birds flock in confused spirals, sea turtles lose their migratory way, and satellites flicker with glitches. This isn't science fiction. It's a window into a real possibility if Earth's magnetic field continues to weaken, distort, or even reverse. The field has never been static. It's a living, breathing entity shaped by the molten chaos beneath our feet. But what happens when that living shield falters? Could we be heading into a geomagnetic reversal? And what would that world look like? Let's take a closer look at Earth's magnetic history. Over the last 20 million years, our planet's magnetic field has flipped its polarity roughly every 200 to 300,000 years. Sometimes it happens more frequently, sometimes less. The last full reversal, known as the Brunhes-Matuyama reversal, took place about 774,000 years ago. That means we're long overdue by geological standards. But here's the twist. Reversals don't occur on a regular schedule. They're chaotic, influenced by conditions in the deep Earth that we're only beginning to understand. When a reversal begins, it doesn't happen like flipping a switch. It's a slow-motion upheaval that unfolds over thousands, sometimes tens, of thousands of years. The magnetic field weakens, fragments, and reorients. During this transitional phase, strange things start to happen. Magnetic north and south may dance across the globe, forming temporary poles in odd places. Some regions might find themselves under a reversed field, while others retain the original orientation. For a time, compasses would be useless, migration patterns would become unpredictable, and the shield protecting us from cosmic and solar radiation could be compromised. Let's talk about that radiation. Earth's magnetic field deflects charged particles from the sun, particularly during solar storms. These storms can hurl billions of tons of plasma toward Earth at speeds of over 1 million miles per hour. Under normal conditions, the field channels most of these particles toward the poles, where they produce breathtaking auroras. But during a weakened or reversing magnetic field, more of these high-energy particles can penetrate deeper into Earth's atmosphere and even reach the surface. Historical records show us just how dangerous this can be. In the year 1859, a massive solar storm known as the Carrington event struck Earth. Telegraph systems across Europe and North America failed. Some operators were shocked by surges of current. Auroras were seen as far south as the Caribbean. Now imagine a similar storm today, except without a strong magnetic field to deflect it. Satellites could be fried. Power grids could go down. Aviation, navigation, and communication systems would all be vulnerable. And in a worst-case scenario, entire cities could experience blackouts for weeks or longer. This isn't just speculation. The South Atlantic anomaly is already a region where the magnetic field is much weaker than the global average. It stretches from South America to southwestern Africa and continues to grow. Satellites that pass through this region often report data glitches or electronic malfunctions. The ISS, the International Space Station, has to take special precautions when orbiting over the anomaly. Cosmic rays and high-energy particles penetrate this weaker patch more easily, threatening onboard instruments and potentially even astronauts themselves. But how does this relate to the core slowdown? If the inner core's rotation affects convection in the outer core and therefore the geodynamo, it could initiate or accelerate this destabilization. Recent studies from geophysicists using three-dimensional simulations show that even a subtle change in core dynamics can shift the balance of the magnetic field. An asymmetric inner core rotating more slowly or in reverse might create localized instabilities. These instabilities can manifest on the surface as weak spots, such as the South Atlantic anomaly, and potentially grow into a full global reversal over time. This is where science meets speculation. Some researchers propose that we may already be in the early stages of a geomagnetic reversal. They point to the steady weakening of the field over the past 200 years. It has lost about 10% of its strength since the early 1800s. Others argue that Earth has experienced similar dips before without undergoing a full flip. These failed reversals are like magnetic false starts, periods of instability that eventually return to normal. One such event occurred around 40,000 years ago, the Lachamps excursion we explored earlier. For a brief time, Earth's field weakened dramatically and reversed, but the reversal was incomplete. Within a few thousand years, the original polarity returned. During that time, the planet experienced increased radiation exposure, potentially leading to extinction pressures and behavioral changes in human populations. Evidence from ice cores, sediment layers, and tree rings paints a vivid picture. Earth's magnetic field is more volatile than we once believed. Still, a full flip is not inevitable. Earth's core is a chaotic system. It could just as easily stabilize again, strengthening the dipole and restoring a more uniform field. The slowdown in the inner core's rotation could be part of a larger cycle, one we simply haven't observed long enough to understand. Our records only stretch back so far, and direct measurements of the field have only been available for a few centuries. In geological terms, that's the blink of an eye. So what are we doing to prepare? Agencies like NASA and the European Space Agency are constantly monitoring magnetic activity. The SWARM satellite trio, launched in 2013, has been instrumental in mapping field changes in unprecedented detail. It's given scientists a clearer view of how the field is shifting and where weaknesses are forming. The data helps model space weather impacts, improve satellite shielding, and forecast potential geomagnetic storms. But the truth is, we are not fully prepared. Our modern society is deeply reliant on electronics and satellites. A major disruption to the magnetic field, whether from a reversal or an extreme solar event, could cascade into a global technological crisis. As we build more digital infrastructure, launch more satellites, and dream of colonizing other worlds, understanding Earth's magnetic heart becomes not just a scientific curiosity, but a planetary necessity. And so the question deepens. Are we witnessing the first signs of a shift that could reshape our magnetic world? Or is this just another fluctuation in a long and mysterious cycle of Earth's inner life? Imagine the world's most crucial defense system, the magnetic field, struggling to maintain its integrity. Over centuries, it has been a silent sentinel, warding off cosmic radiation, shielding us from the full brunt of the sun's energy, and ensuring life on Earth continues to thrive. But what if that shield, quiet, ever-present, began to flicker, to wane? What if, instead of a reliable guard, it became a fragile barrier, one that could break at any moment? Could the very world we know, our modern civilization, our interconnected lives, be at risk? To truly grasp the stakes, we must delve deeper into what a magnetic reversal, or even just a dramatic weakening, could mean for Earth. We know from history that such events have occurred before. The question is whether the conditions are ripe for another one. So let's step into the future, and into a world that might seem both familiar and wildly different at the same time. The most immediate consequence of a weakening or reversal of Earth's magnetic field would be the increased exposure to solar and cosmic radiation. Earth's magnetosphere, the region of space around the planet controlled by the magnetic field, acts as a protective shield. When charged particles from the sun or deep space approach Earth, the magnetosphere deflects most of them. The particles are funneled toward the poles, where they create the stunning auroras we often see in the far north and south. Without this shield, however, the radiation would reach deeper into our atmosphere, possibly even touching the surface. High altitude. Flights, particularly those that traverse polar regions, would be among the first to experience these effects. Commercial airlines could be forced to change their flight paths, flying at lower altitudes or rerouting to avoid higher radiation levels. This would increase fuel consumption and operational costs and could pose health risks to airline passengers and crew. If the magnetic field weakened enough, some experts speculate that airline travel might become limited to certain latitudes, especially during solar storms. But it's not just human travel that could be affected. Satellites, which are the backbone of our communications, weather forecasting, and GPS systems, are particularly vulnerable to radiation. When the magnetic field weakens, these satellites become exposed to higher levels of solar and cosmic radiation, which can short-circuit delicate electronics. We've already seen evidence of this. Satellites in orbit passing through areas of weakened magnetic protection, such as the South Atlantic anomaly, suffer from unexpected malfunctions and data errors. A full-scale geomagnetic reversal could expose satellites to catastrophic levels of radiation. In such a scenario, communication networks might fail, weather monitoring could become unreliable, and navigation systems could go dark, impacting everything from smartphone apps to international shipping routes. It's worth considering the broader implications of such failures. Imagine a world where GPS stops working. Planes, ships, trucks, and even autonomous cars rely on satellite-based navigation systems to stay on course. Without these systems, global trade would grind to a halt. Emergency services would be thrown into disarray. Precision agriculture could falter. The ripple effects would be felt worldwide. And then there are the power grids. Modern power grids are more vulnerable to geomagnetic disturbances than we'd like to admit. High-energy solar storms, or even a weakened magnetic field that lets more radiation reach the Earth, could induce powerful electric currents in power lines. These geomagnetically induced currents can overload transformers, leading to blackouts. In 1989, a powerful solar storm knocked out power across large parts of Canada. The blackout lasted 9 hours and cost the utility company over $100 million in repairs. If the field were to weaken or shift dramatically, the risk of such events would increase exponentially, threatening everything from household appliances to entire cities. The damage from a geomagnetic storm could cost the global economy hundreds of billions of dollars. But there's another aspect to consider: the impact on Earth's climate. While a geomagnetic reversal might not directly alter the Earth's temperature or weather patterns, it could interact with our atmosphere in unexpected ways. The magnetic field plays a role in protecting Earth's upper atmosphere from the stripping effects of solar wind. Without this protection, the solar wind could gradually erode our atmosphere, potentially leading to a gradual decline in atmospheric pressure over millennia. This wouldn't happen overnight, but over the course of thousands to tens of thousands of years, such a gradual loss could have dramatic consequences. In extreme cases, this could potentially accelerate the loss of ozone in the upper atmosphere, allowing more ultraviolet radiation to reach the surface. While Earth's atmosphere is still relatively thick and protective, the loss of this protective ozone layer would increase the incidence of skin cancers, cataracts, and other health problems. Plant life could also suffer, as the increased UV radiation would disrupt photosynthesis and reduce crop yields. Another facet of this puzzle involves the deep oceans, specifically how the magnetic field interacts with marine life. Some species, particularly migratory animals like sea turtles and salmon, rely on Earth's magnetic field for navigation. These creatures have evolved to detect the magnetic field and use it as a natural GPS system. A weakened or reversed magnetic field could disrupt their migratory patterns, leading to disorientation, population declines, and ecosystem imbalances. This may seem like a minor issue in the grand scheme of things, but remember, marine ecosystems are some of the most productive on the planet. If these ecosystems were to falter, the global food chain could be affected, leading to a potential crisis in seafood supplies and altering the balance of the oceans. Yet, even with all the potential risks and uncertainties, we must remember that life on Earth has faced dramatic shifts before and adapted. The planet has lived through numerous geomagnetic reversals in its long history. Life on Earth didn't just survive the Lachance excursion or the Brunhes-Matuyama reversal, it adapted, evolved, and continued to thrive. These events didn't cause widespread extinction, although they did coincide with other environmental factors that may have led to changes in life on Earth. Scientists are actively working to understand the dynamics of Earth's magnetic field and its potential for future reversals. With more data from satellites and ground-based observatories, we're building better models of the core's behavior and learning more about how these deep Earth processes influence the surface. While we may not have all the answers yet, one thing is certain. Earth's magnetic field is far more dynamic and complex than we ever realized. As we continue to study the field's fluctuations, scientists are looking for ways to protect our technological systems from the worst effects of geomagnetic disturbances. Hardening satellites, improving grid resilience, and strengthening our weather forecasting abilities are just a few steps that could mitigate the risks. But one thing is clear. This is a global challenge. If Earth's magnetic field were to undergo a drastic change, it would not only affect specific regions but the entire planet. So the question remains, are we ready for a magnetic future that might not look like the world we know today? Are we prepared to adapt to a world where the sun's rays could shine a little brighter, where our navigational tools might fail, and where the very animals that share our planet with us are confused by the changes? As we peer into the future, it's not just about the Earth's magnetic field, it's about the resilience of life itself. The magnetic field we've come to rely on, our planet's silent protector, is not as constant as we once thought. It's a living, shifting entity, governed by the fiery, dynamic processes beneath our feet. We've explored the potential consequences of a magnetic field collapse, a geomagnetic reversal, and the far-reaching impacts such a shift could have on our world, from disrupted navigation systems and malfunctioning satellites to altered climates and confused animals. But there's one more question we must confront. How likely is this future? And are we truly helpless in the face of this colossal force of nature? Let's consider the possibility of a magnetic reversal. While we've seen signs that Earth's magnetic field is weakening, it's important to understand that geomagnetic reversals are a slow, complex process. There is no clear-cut timeline. The process could take thousands, perhaps tens of thousands of years to unfold fully. As we stand today, we're not necessarily on the brink of a reversal, but the signs suggest that something is happening beneath the surface. And though this process is slow, it's not without warning. Scientists are keenly aware of the subtle changes occurring in Earth's magnetic field. Monitoring satellites, ground-based stations, and data models are all part of the effort to understand what's at play deep inside the Earth. Even as we gain more insight into the behavior of the magnetic field, it's crucial to acknowledge that not all changes are catastrophic. While the reversal of the magnetic poles could pose challenges, humanity has faced and overcome natural disasters, technological failures, and environmental shifts before. It's a testament to human ingenuity and adaptability, the same qualities that have helped us survive ice ages, volcanic eruptions, and asteroid impacts, could one day help us navigate the challenges of a shifting magnetic field. This is where science, technology, and innovation come into play. Just as our ancestors learned to adapt to the changing environment, so too can we. Modern technology provides us with the tools to mitigate the impacts of a weakened magnetic field. By hardening our infrastructure, particularly satellites and power grids, we can reduce the risks of geomagnetic storms. Advances in materials science may offer new ways to shield sensitive equipment from solar radiation. Furthermore, international collaborations and space agencies like NASA and the European Space Agency are already studying these phenomena in great detail. The research is ongoing, and with each passing year, we come closer to understanding the true nature of our planet's magnetic life. Imagine a future where humanity learns to coexist with an unpredictable magnetic field, not as passive bystanders, but as active participants in managing its risks. Just as we track space weather and prepare for solar storms, we could develop new technologies to shield our power grids, protect our communication systems, and reinforce our satellites. This could involve everything from creating stronger and more resilient satellite shields to launching new technologies designed to detect geomagnetic shifts long before they reach critical levels. But what about life on Earth? While the effects on ecosystems, including migrating species and the potential for atmospheric erosion, might seem concerning, we must remember that life on this planet is remarkably resilient. Species have adapted to changing climates, magnetic anomalies, and cosmic radiation for billions of years. It's not about whether life can survive, it's about how we respond to these changes. The question becomes, are we prepared to protect our planet's delicate balance in the face of these challenges? The magnetic field, despite all of its uncertainty, is a reminder of the dynamic, ever-changing nature of our planet. It is not a constant. Like the other forces that govern life on Earth, the forces of plate tectonics, volcanic eruptions, and even the sun, it reminds us of how fragile and interconnected we truly are. This is a humbling truth, one that teaches us to respect the forces of nature and the need to safeguard the delicate systems we rely on. It's not just about surviving a magnetic reversal, it's about thriving in an ever-changing world. As we look ahead, one question continues to linger. How will humanity rise to meet the challenge of a changing magnetic field? Will we become passive victims of an inevitable force, or will we use our ingenuity, our creativity, and our resilience to adapt and overcome? This is not a story with a clear ending. The future of Earth's magnetic field is uncertain, full of unknowns and variables that we may not fully understand yet. But one thing is for sure, our ability to adapt, innovate, and work together will determine how we navigate the challenges ahead. The magnetic field may shift, the poles may reverse, but humanity's will to endure, to learn, and to thrive, despite the vast, unpredictable forces of nature, will always remain. And that, perhaps, is the most fascinating mystery of all. Not what the future holds, but how we will rise to meet it. If you found this video intriguing and want to dive deeper into the mysteries of our universe, be sure to subscribe to Cosmic Whispers. Like, share, and comment below with your thoughts on the Earth's magnetic field. What do you think? Is a magnetic reversal in our future? Or is it just another scientific curiosity we need not worry about for centuries to come? Let us know your thoughts and keep exploring with us. Thank you for joining us on this cosmic journey, and remember, every great discovery starts with curiosity. Stay curious, and we'll see you in the next video.